University of Massachusetts at Amherst, Chemical Engineering, Polymer Science 757, Polymer Rheology, H.H. Winter, Lecture 21A. The constitutive equation of Arthur Lodge had a tremendous influence on the development of rheology in general. It's a very simple model which models several important phenomena which we know about polymer melts and polymer solutions. So it is good to understand that in a little more detail. Arthur Lodge, by the way, will have his 70th birthday this year. So he's still around in meetings, and we have his friends put together an issue in Rheological Acta for him in honor of his birthday and his activities and his contributions. So you maybe should look at that. So this is his equation, which he proposed in the 50s and wrote a book about in 64, Rubberlike liquids. It has one material function, which is called the memory function. We know that from linear viscoelasticity, and it secondly has a strain tensor in here, and Arthur Lodge picked the finger strain tensor because that type of tensor came up from the theory of rubbery solids, and he is really modifying the theory of solids to apply them to rubber-like liquids. That's why he picked this name for the system. He derived this equation in a very elegant fashion from molecular arguments also. But let me put a simple linear superposition principle forward, which gives us this equation. We would look at an example, for instance, extrusion through a die, where a material element moves along this path. And when it's at this position, say, we would like to know the stress. Now, the stress here is a function of the strain history, some function we would like to use a constitutive equation to correlate or to relate this strain history with the stress here. For doing that, we look at an infinitesimal material element as it moves along this path. At time t, it is here, and we would like to know the stress here. At some instant in the past, t prime, for instance, this element is moving along here, and during a short incremental time, delta t, there will be some network junctions being formed. We assume that the polymeric liquid is able to form network junctions. Nobody has seen a junction. They're sometimes also called entanglements. Now, Lodge just said the requirement is that two molecules are able to join at one point and move together for a time which is longer than the fluctuation time of that molecule to reorganize. So somehow the reorganization of the overall molecule is hindered because those two, because this molecule is somewhere connected to a neighboring molecule. And there's a creation rate of those junctions and a loss rate. They are falling apart. The assumption really is that they fall apart in a first order reaction. So in this model now, we assume that junctions are created during the time interval delta t prime. And these junctions form a network which partially survives the strain from here, from t prime to t. And then they are subjected to the strain described by the strain tensor here, or finger strain tensor. And a stress will be the consequence. So that's the basic procedure in this model. The number of junctions generated at this short time interval delta t prime at t prime is the rate of junction generation in dot multiplied with the time interval delta t. So that's the number of junctions generated at that time. Those junctions from here on will start falling apart. The assumption is that they fall apart in a first order reaction. So they are decaying in an exponential function, like here. Lambda is the time constant of the decay process. If lambda is constant, then this can be put outside, and it's just t minus t prime over lambda. and the minus sign is up in front. I kept a variable time constant in here because one purpose of the derivation I'm going through is to look at the possibilities of temperature effects where the time constant is variable. We would like to look at isothermal flows of a large rubber-like liquid fluid. So let's keep it variable for the moment. This was the number of junctions generated at this short interval. This is the number of junctions now which survive the flow from T prime to T. And they are contributing to the stress. If you take the number of junctions at that time, dt belongs to that also, multiply them with kt, and multiply them with the finger strain tensor, then you have the stress contribution of those junctions as described in rubber theory of Treloar, for instance. The stress which originates from that is, of course, only the stress contribution of that short time interval dt. The superposition is the next step. The linear superposition gives us the total stress. We're just superimposing all stress components from minus infinity to the current time t. So those stress components are expressed by the term which we just derived, the number of junctions generated at t prime and still surviving this the time interval from t prime to t multiplied with kt and multiplied with the finger strain tensor. And again, if lambda, if this time constant is really a constant, then the integral reduces to an exponential function. The equation which we obtain for after all this looks something like this. A further assumption is introduced, saying that we not have just one species of junctions, but a whole range of different types of junctions, say of type I, and we have n of those, and each of those have their own relaxation time. And this gives us the relaxation time spectrum, because of the spectrum of junctions we are looking at, relaxation time spectrum, and the whole term here is the memory function, which in conventionally we call just m as a function of t prime and t. And since this is an integral, I just take those independent function. But if lambda is constant, this would be just t minus t prime as a variable, multiplied with a finger strain tensor. This type of derivation came developed over some time, but Lodge formulated very clearly in '56. But older ideas had been building up. And I gave you a list of references where you can read about all those details. When I just mentioned the name in a year, in this list at the end of your handout, you can follow up if you would like to. In this equation, we kept the relaxation time as a variable. This allows to describe temperature effects because the relaxation time would be shifted from a reference temperature level to an instantaneous temperature level. T might be a function of time. And the memory function then is expressed in terms of GIs, which are temperature dependent, and the exponential function here. This is why this is in an integral form. Morland and Lee and somebody before them developed this type of model. So that's very well established in describing non-isothermal rheology. In the limit of very short times, a liquid which relaxes very quickly, the large rubber-like liquid equation reduces to the Newtonian liquid equation. Now I want to show that to you. The derivation doesn't require the entire relaxation time spectrum. We just take the longest mode here and say that if there are some shorter modes involved, that's okay too. But we would say the memory function is approximated by the most important mode, and the relaxation time of this mode is said to go to 0, to be very, very small. If the memory is so short, then only the immediate vicinity of T is contributing. Everything further back in the past has been forgotten. Let me write this down in a little more detail here here at the blackboard. If we describe the stress at time t in terms of an integral from minus infinity to the current time t, and we are splitting up this integral into two parts. So we take a first integral from minus infinity to t minus some increment. And large rubber-like liquid equation would give us here the finger strain tensor dt prime and the memory function, plus now the second part of this integral. This is from t minus delta t to t, taking the memory function, finger strain tensor dt prime. And those are the tensors which we are looking for. The longest relaxation time in the limit of going to be very, very short will be shorter than this. So, or you could say this is in delta t is in the same order of the longest relaxation time. It's just a very, very short increment. So all the action will be occurring in this integral, and this part of the relaxation time spectrum is unimportant because the memory doesn't go far enough back, right? So we are only dealing with this part of the strain tensor and of the memory integral. The strain tensor in this integral where t prime is very close to t, we're talking about very, very small strains. Now, the strain tensor, finger strain tensor, in this case can be approximated by 1 plus s times the rate of deformation tensor, which would be 2 times d, and we can evaluate this at time t. And s is just a short notation of the distance in the past, t minus t prime. S, in fact, is going to 0 in our picture because we're talking about very, very small strains. So in that limit, I introduced that here in the equation. I just took the finger strain tensor reduced as written on the blackboard, introduced that into the constitutive equation. We can take the whole equation from minus infinity to t because most of the history is dropping out anyway. We are representing the finger strain tensor as such, and then we integrate everything, and we find that the stress is given by an isotropic contribution plus a viscosity term times 2 times d. The isotropic contribution in an incompressible liquid doesn't contribute, and the extra stress tensor can be expressed as a viscosity times 2 times the rate of deformation tensor. So the limit we were looking for is there. The large rubber-like liquid reduces to the Newtonian liquid in case of a very, very short relaxation time. So this is okay. Now I would like to move to large deformations and discuss constitutive equations for large deformations. In large rubber-like liquid, we took a memory function which was given by linear viscoelasticity already. So we had all the time dependence characterized. It's easy to determine the relaxation time spectrum, so we know what's happening in transient experiments. The molecule, in this case, is expected to be in an equilibrium state. It's somewhat coiled, and the strain is small enough so we don't disturb that structure sufficiently. The large rubber-like liquid is good up to strains of 2 or 3, which is fairly large. I was surprised that it holds to strains like that. But beyond that, we definitely have to put non-equilibrium properties in there. We have to account for the flow-induced orientation that somehow changes everything. And the question now is, how can we change our models, our constitutive equation, to incorporate this effect? A popular approach here starts with the integral models, and I just drafted this here. We would take a single integral model, because we're looking for a simple constitutive equation, where we have a memory function of some type and a strain function of some type. And several proposals can be made now to accommodate large strains in the system. We could modify the strain measure. Instead of using the finger strain tensor or core sheet strain tensor, you can use any other type of large strain measure. There's an infinite number of those. Doi and Edwards proposed a strain measure here which comes out of molecular arguments. They're looking at flow-induced orientation of molecular strands, and to model that, they need some strain measure, and that determines this tensor Q. Muto will talk about this type of approach because it's closely associated with molecular dynamics. So in the moment, I don't want to touch this in greater detail. The second proposal is modification of the memory function. We will take this integral and somehow leave the strain tensor as in the large Rubberlike liquid as a Cauchy tensor or a mixture of Cauchy and finger strain tensor. But we still have to accommodate somehow the strain effects, and we would do this by changing the memory function. The rest of this lecture I will spend on this type of approach. It will be an empirical approach with the objective to modify as little as possible to get to obtain a description of the experimental observation. And then with that format, one can expand and do some fine-tuning. But we would like to go as far as possible with little modification. The third approach would be modification of the differential model. This equation can be, when you start, for instance, with a large Rubberlike liquid, can be expressed in differential form. And then one can start modifying those differential models. I won't talk about this today. Well, if there's time at the end, I will give a few examples. But that's not the main emphasis of the lecture today. Also, my colleagues, when they teach rheology, have a larger emphasis on differential equations. So as years come, you might drop into rheology lectures and see more details about the differential models versus the integral models. So in the moment, I would like to stay as intensely with the integral model and see how far we can push that. The strain energy function concept has been applied to polymeric fluids, and it led to the Bernstein, Kearsley, and Zappa's model, a constitutive equation proposed in '63. In fact, Zappa's got the Bingham Medal of the American Society of Rheology last year for this contribution, which is quite nice, as you will be seeing. The strain energy function, we discussed that a little bit last time when we talked about rubbers. So the strain energy function basically gives the energy per unit volume, which is associated with a strain. We are taking an infinitesimal strain, so the strain tensor is given between T minus delta T and T, and that's multiplied into the stress, and the product is the energy per unit volume, which is involved for this deformation. And in rubber, that would be okay, but in a polymeric liquid, the loss of junctions, or whatever you want to call this, has to be accommodated in the fading memory. So the proposal was to express this strain energy function in terms of a fading memory of a memory integral. So this is a function which is decaying in time, but it's also depending on the invariance of the finger strain tensor and the Cauchy strain tensor. The invariants are all coupled. You can take any two invariants. I took the first one of the finger strain and the first one of the Cauchy tensor. You can take the first invariant of the finger strain tensor and the second invariant of the finger strain tensor and rearrange everything accordingly. But I took those because in the strain energy formalism, we have this the first term associated with the finger strain tensor and the second term associated with the Cauchy tensor. So this function here has been introduced into the strain energy function model, which we had last time. So and then instead of permanent junctions, we have the contribution from this memory function here from this kernel here, first derivative with respect to the this invariant with the finger strain tensor, and then second derivative with respect first invariant of the Cauchy tensor. There's a factor 2 in both. If you would go through the derivations, I can show you how that is. But in the literature, you can see how this has been derived. This model has no specification yet about the kernel function of this memory integral. We have no clue how to describe that. So with network models, the general format has been provided, but it's not specific enough. Many people worked on this type of model. Boak and Doty, for instance, 67, Tanner and co-workers, and Yen, McIntyre, Wagner, Osaki, they all proposed a specific kernel where this function, this was our decaying function in time, was broken down into a time function and a strain function. Now, this time function would come out from linear viscoelasticity, and the strain function has to be determined somewhere with experiments. In 71, Osaki's experiments were available, so that type of approach would have been logical at that time. But note, Boak and Tanner were, even before seeing those experiments, were fairly early. They, in fact, didn't have enough experimental data. When Wagner looked at this approach in 76, he had substantial amounts of experimental data of Meissner, Laun, the BASF laboratory, and he was the one writing in a set of beautiful paper, very clearly written papers. He was the one showing that this concept is indeed fruitful, that this leads to very good agreement, very good predictions, agreeing with the experiments. So sometimes the model is called Wagner model because of his very nice papers. And Osaki was, of course, also involved in that at the same time as Wagner was doing that. The stress now in this case, where the memory function is factorized, is given by the memory function of linear viscoelasticity plus a strain term, and you could say that's already a modified strain measure because all of this here depends on strain. We are just combining a finger strain tensor and a Cauchy tensor. In fact, this first one should be a finger strain tensor, so it needs the -1 in that notation. Okay, that's it. Let's do some exercises with that factorized memory function so that you see how it works, what it can predict. The model, again, looks something like this. We have this memory function for the time dependence. And the strain function, let's call those now just H1 and H2 for simplicity. Those really incorporate the part of the strain energy function, which the strain part of the strain energy function, the derivative. It hasn't been specified anyway, so why talking about derivatives? We just use those as two functions, as functions of the invariance. And we would like to apply this equation to shear and extension. I wrote down some components which you can analyze. You can look at the shear component or the normal stress differences, and you can do the same thing in extension. So maybe I should put this on the side so that we can come back to this equation several times. The first logical experiment would be the step strain experiment. We know how to analyze that. It's familiar. So let's see how this equation is handled when describing the step strain experiment. We take the BKZ model. In step shear, prescribed is the strain, which is suddenly imposed and then held constant. And the stress response now is given by the derivative here with respect to the invariant of the finger strain tensor minus 2 times the derivative in Cauchy tensor, plus there is a contribution where we have to look at the integral. This is the contribution of the rest period from -infinity to 0, and then there's a contribution from 0 to t which is 0 because the strain is between some time here and time t is 0. No additional strain is introduced. So that contribution is 0. And then we should mention that there's an isotropic contribution. I forgot this original, but so just added it on here at the end. We are looking at shear stress and normal stress differences where this is changed anyway. Okay, and now we evaluate this integral by splitting this function into time dependence and strain dependence. It reads in the following here, for the finger strain tensor. Let me go back here in this here. We're talking about the shear stress, has no component here, but for the finger strain tensor, it just has gamma times H1 times the first part, minus, and then minus gamma times H2. So gamma comes in the sum of H1 and H2. And that's what we are seeing here for the shear stress. And gamma is equal to gamma 0 in this range. And this is just reduced to h of gamma. We're just contracting those two contributions in a single strain function. And this is the result which we would have expected, and that's the result which Einaga and Osaki got in their experiment. So what's the form? What is the from experiments now we can determine h of gamma and can see how big that is. We know already that at very small strain, this should reduce to 1 because there's no strain effect. The equation should reduce to the equation of large. And so at very small strains, if gamma is equal to 0, h will be equal to 1. And then for some time, it will stay constant. There's a linear viscoelastic range up to strains of 2 or so. It should not be affected. And then it will be dropping, and then will be very low. That's what's causing the shear thinning phenomena in the polymeric melt. There have been many proposals for this type of function. For instance, Wagner said, why not take a simple exponential decay here, just with increasing gamma, it should go down. Now, in a decay like this, the function would drop immediately and then would go down. It turns out that these deviations up here are not too important, and the predictions with that simple equation is very, very good already. Osaki at the same time proposed a model where he added 2 terms, 2 exponential decays, and he modeled polymer solutions with that and found very good agreement. Later on, Papanastasiou, Scriven, and Markosko proposed a sigmoidal type of function where they found that this S shape can be described very nicely if they use a format like that. This was in '83, and we saw that, and we talked with them doing their experiments. And so Sosky, when doing step strain experiments, he modeled his data with the same function, but he realized that 2 is not the most appropriate. It's closer to 1.5 or so. So he kept this as a free parameter. So with this type of approach, you can really model any of those experimental functions very nicely. All of this is restricted to shear flow. But let me take a short excursion and talk about invariance. So this is an aside, and let me come back to the step strain experiment in a moment. But we are always talking about the strain invariance and how they influence the formulation of constitutive equations. In shear flow, the strain invariance, say for the finger strain tensor, are given by the trace of that matrix given by 3 plus gamma squared. And the second invariant of that finger strain tensor has, again, the value 3 plus gamma squared, if you follow the definition of that second invariant. The third invariant is equal to 1 when taking a constant constant density for the fluid. In the same fashion, if you take the Cauchy strain tensor and calculate the first invariant and the second invariant, they are also 3 plus gamma squared in all cases. So the result is that for shear flow, 3 plus gamma squared is the only invariant which matters. In general, you will find that for all plane flows, the invariants are equal to each other. The first and second invariants are equal for any plane flow. It's not only limited to shear flow, but you can check that in an exercise. So for all plane flows, somehow our constitutive equations will be simpler because we don't use two invariants as parameters when formulating constitutive equations. We only have one parameter in this case. That's an advantage when describing shear flow. But it's also a big disadvantage because the shear flow experiments are so well developed that we would like to characterize our liquids in shear flow. And here, when looking in the invariants, you can see that the information will be limited when looking at shear flow. There's something missing which we only gain when we go to extensional flow or to more complicated kinematics. So much about the invariants. Let's formulate the strain functions in terms of the only invariant which we are talking about. I'll just call it I and use Wagner's single exponential with gamma being just the root of I minus 3, or Osaki's two contributions here, or Papanastasiou's form here in this form with invariant. I think Larsen formulated that. And Soski's formulation also is then equivalent, using an invariant here. For shear flow, it's just one invariant. If we go to complicated flow, we don't know what will be expected. Soski, in his experiments now, where he measured the strain function, the effect of large strains in a step shear experiment, found the following. He looked at long linear chains which are just linear and chains which are branched. And he found that there's a big difference in the strain function. This is just log h. Here it would be 1 at small strain as a function of the imposed strain. This phenomenon is attributed to the molecular structure. You can imagine that a molecule which is long chain branched, if I take a long linear chain which has all kinds of side chains, that this chain, when subjected to a deformation in a matrix, will be anchored in the matrix, and it will not be able to relax very quickly, while a chain which is just linear will be able to retract much more freely in that matrix. So the large strain behavior will be very different for a linear molecule and a branched molecule, and Soski found that in the strain function, which was a very interesting piece of information. We followed up on this and found that a linear polyethylene, this upper curve is a branched polyethylene. A linear polyethylene is also following the same curve as a linear polystyrene. So it seems to be a general feature of that molecular architecture. Shall we stop here for a moment, Becky? Is this okay? Before I go to the next flow, I will discuss startup of shear flow. So far, that was the easy, the less laborious exercise. We will see how. University of Massachusetts at Amherst. Chemical Engineering, Polymer Science, 757, Polymer Rheology, HH, Winter Lecture 21B. The next exercise I want to go through with you is the startup of shear flow in a polymeric liquid. We could do this on the blackboard, so just to have a little change. So we talk about an experiment where the shear rate is constant beyond a certain time. So this is the time we are looking at this material. And the stress which we would calculate would be shear stress, first normal stress difference, and second normal stress difference. Let's start with the shear stress. So the shear stress as a function of time is given by an integral from -infinity to the current time t times the memory function evaluated at, say, t minus t prime. If we talk about isothermal flow, just the time difference is important. If you have variable relaxation times, you have to use a more complicated format. And then we would use something describing the strain. And in this case, when you look at the, here we have H1 times gamma, here gamma between t prime and t, plus H2 of times gamma between t prime and t dt prime. This would be the finger strain contribution, and this would be the Cauchy strain contribution. We can contract these two things into just one strain function, h of gamma, multiplied with the total strain between t prime and t. And the strain is defined here. The strain between t prime and t is just an integral from t prime to t of the strain rate at some intermediate time times t double prime. So that's the formalism we are going to use. The first step would be the separation of this integral into two parts. We have the rest period where the shear rate is equal to 0. And in this rest period, this is from -infinity to the current time t. The strain is given, this strain, if we evaluate this function, is given as no contribution here, and then all the strain happening between 0 and time t. So the strain is just the constant shear rate which we are imposing times the total time of the experiment. We really want to calculate the stress at some time out here. And this is the rest period. And the flow period, wait a minute, the rest period is here up to time 0. And the flow period is the time between 0 and the instantaneous time. T would be some time here, t prime to the current time t. And the strain in this case is equal to the constant shear rate times the time interval. This is t minus t prime. To introduce that into the integral here, we are using two parts. So we have the stress to tau to 1 is equal to the first integral from -infinity to 0 times the memory function, t minus t prime, times the strain function. Now, this is h of gamma. Let's leave that for the time being in here, times the total strain, which is gamma dot 0 times t dt prime. This is the first integral for the contribution of the rest period. plus the contribution of the flow period, which is an integral from 0 to time t of the memory function t minus t prime of h of gamma gamma dot 0 t minus t prime dt prime. To proceed from here, we have to introduce some specific forms, otherwise we couldn't integrate this function. And my proposal is that we use a memory function t minus t prime being equal to the discrete spectrum, where I is equal to 1 to n, discrete spectrum, of gi over lambda I e to the minus t minus t prime over lambda I, the discrete spectrum. This, we don't lose any generality because that spectrum is on an equal footing to the continuous spectrum. We can go back and forth from one to the other. So when using that, we just want to integrate those equations, want to have an easier life. And the second assumption, or the second thing we introduce, really is an assumption. We will use Wagner's strain function because that's easy to formulate. We will use h of gamma being equal to an exponential function of minus n to the total strain, which is introduced in here. So in this here, in this case, we have e to the minus n gamma dot 0 times t, and in this case up here, we have e to the minus n gamma dot 0 times t minus t prime, putting in the individual strains. You see that the first part is very easy to integrate. It has t prime only in the memory function. Everything else can be moved outward, up front. This integral has t minus t prime in most cases. So we will rewrite this by introducing a substitution for s is equal to t minus t prime. So in the next step, we introduce all those. The summation can be put up front. We are interchanging the integration and the summation in our approach. So we have the summation and gi lambda I are also not affecting any of the integrals. We are moving this part out front. And you also see gamma dot 0 appearing in both integrals. So we have gamma dot 0, and this is equal to the shear stress, tau 2, 1, multiplied with some term. Remember that the viscosity, which you would calculate from large Rubberlike liquid, would be equal to gi lambda I summed up over all modes. We have modes from I equal 1 to n. So in the small strain limit, we should have gi times lambda I, and the modifications will show that this is really the limiting case of linear viscoelasticity. The next term here will be, the first integral now from, in fact, I can pull things outside even. I can pull t times e to the minus n gamma dot 0 t outside, and have an integral then from minus infinity to the current, this is to 0, of this function here, e to the minus t prime over lambda I. dt prime, that's the only part which is left over from the first integral, plus now in the second integral, where we replace t minus t prime with s. So we have e to the minus s over lambda I times this memory function. This is e to the minus n gamma dot s. So s is occurring in both terms when we are summing those up. Will be combined. Times s ds. And for the integral, we have to calculate the bounds. And the bounds, in this case, are really going from 0 to t. You know, we're going backwards in that type of magnitude. This can be integrated. Well, we have here summation. And then we calculate the viscosity from that. It will be, when you integrate this, we have a term with lambda I squared coming in. So the gi lambda I will be out front in the limit of small strains. So let me see where we are. Yeah, in this derivation here, don't want to write everything on, on the blackboard. You can see that S can be put outside here, and it's just multiplied with a constant. And when you integrate this, here you get really 1 over this function, and a square term comes in because it's SDS. While this integral is integrated straightforward. Actually, the first integral which we are dealing with is this one, is lambda I times this function, and the second integral is having this front factor and has a few more terms involved. All of this is now rearranged. The first integral is giving us a decaying time function. And the second integral gives us 1 over a constant plus another decaying time function. So this is giving us all the transients. And again, this can be rearranged further. We can put this as a common factor outside, so we have two terms added up. So we have to put this here, this bracket square here, we have to put this out front. And now the result from this modeling calculation is the following. The shear stress is given by the shear rate times gi lambda I. That's what we would expect for the viscosity. But these are divided now by a term which contains the shear rate. And this first function, this first term, is multiplied with 1 plus a transient term. So after long times, this second term will be dropping out, and the steady shear viscosity is given just by shear stress over shear rate times this front factor. So note that in our solution, this front factor is equal to the steady shear solution. And the transient part looks complicated because we really want to have a very complicated response which we want to model. We want to have, say, the shear stress tau to 1 over the shear rate is not following this nice evolution of linear viscoelasticity, but it goes through a maximum and then it levels off. And this term here, this magnitude here, that's what we have. This is the sum of gi lambda I divided by this expression squared in the bracket. That's the steady shear viscosity which we're calculating. And the transient part has to follow this overshoot. For a long time, this term here has called an overshoot, and people wondered why in startup of polymeric liquids the stress is very large for quite some time. And they just couldn't figure out how to model this type of strain hardening. Only much later, when data became available and the modeling became more quantitative, people realized that the viscosity in the linear viscoelastic case is actually much higher, and this overshoot is associated with a shear thinning phenomenon. It's really a falling behind. It's not a stress overshoot associated with hardening of the material. So it's a shear thinning phenomenon, and that's the way I'm talking about this, and everybody talks about this nowadays. But 20 years ago, people went to meetings and wondered where this large stress came from, where this overshoot was coming from, and just the wrong concept, the wrong idea made it very difficult to model this type of behavior. This overshoot has been described very, very well by experimental data. I will pick some data from the literature, but before doing that, the shear stress always comes in the data comes together with the normal stresses. So let's look at the development of the first normal stress difference in the startup of shear at constant rate. It's just a counterpart to the shear stress which we just looked at. The first normal stress difference is given by gamma dot square times the time between T and T prime here squared. This is really the strain squared times H1 plus H2. Now both of them come in, they are lumped together, so we're just using one H in this case. We cannot distinguish between the two. Model them with a function like here, like Wagner proposed, and we take a discrete spectrum for the relaxation times, introduce everything here, so we have the exponential function from the time dependence and the exponential function from the strain dependence. That's actually why Wagner looked at this simple representation. It's so easy to combine. And S squared occurs because the strain is squared. Here I only want to calculate the steady shear response to the first normal stress difference. We could do startups and have all those transient terms. I didn't want to do this here. I just took the total integral from minus infinity to current time t and said, during all this time we have a constant shear rate, and that simplifies the calculation, and we won't get the transient here as a result. So the simple formulation here, the simple kernel can be rearranged. We put everything outside which doesn't belong into, it doesn't have any S dependence. This function here with a constant here in the exponent coming in with the S. Now, this function can be integrated. We just replace this with, substituted with X, and we have a front factor here, gi over lambda I, with multiplied with this one here. It comes in with a third power because we have S squared ds, and the simple value of this exponential function is 2. We introduce that solution and find that the first normal stress difference is equal to 2 times, here this is where the 2 comes in from this integral, 2 times gi lambda I squared. That's what we would expect for a small strain behavior, divided by the bracket, same function again with the shear rate and the individual relaxation time, times n to the cubed. This guy. With experiments experiments with polystyrene and polyethylene gave n values in the order of 0.1 or 0.2, so it's very small. So you can, by fitting experimental data, you can determine the value of n. Laun, in his paper of 1978, used these equations and checked his data. This is startup of shear flow where the shear stress has been measured. The maximum is not very visible when talking about when plotting this in a log-log plot. And he also had the startup of the first normal stress difference. You can see that the maximum occurs at about twice the strain as the maximum in the shear stress. He performed experiments at several different temperatures and normalized his data by an elegant way of plotting here the strain by shifting things. But I won't go into details. His reference temperature was 150 degrees, and shear rate was 1 seconds to the -1 for the data, but he could shift everything into each other, which is an interesting property of polymeric materials. You can see the line, which comes from the equations, which you just saw, and the dots are the experimental value. So those are transients. Well, for the shear stress, we saw the transient. For the normal stress, I only had the steady state value. Laun shows the steady state value. For the first normal stress difference, it is a decaying function. The shear rate is going down like this. And the shear stress, or the viscosity, shear stress divided by shear rate, viscosity has a 0 shear rate region, and then it goes down like this. The lines are given by the model, by this very simple BKZ model with factorized strain function. It is really it's amazing that such a simple model is able to capture the basic features of shear thinning in such a direct way. And that's the reason why this equation is so popular. It's easy to handle, and you get so much out of that. You can describe a lot of transient phenomena and a lot of steady state phenomena in a quantitative way without really suffering too much in calculations. Problems arise when you go to more complicated flows. So far, we looked at plane flows where the invariants were all the same, and a single invariant was sufficient to describe the behavior. But questions are, what happens if the first invariant is different from the second invariant, or the first invariant different from the first invariant? One for the Cauchy tensor, one for the finger strain tensor. If those are different, what do you have to do to accommodate that? And then which format should the strain function have? What should you do in general? Wagner proposed to use an invariant which combines the first and the second invariant, or combines the invariant of the Cauchy tensor and the Cauchy tensor invariant of the finger strain tensor. On additional parameters introduced by doing that, he has this alpha, which he can adjust to model data. Indeed, he looked at the startup of extensional flow. Uniaxial extension is a flow where those two invariants are different from each other. So he had startup of uniaxial extension. The classical data from Meissner and from Laun of Münstedt were available at that time. So he looked at this data and modeled them, and he found that the strain function, which he should use in this case, should be of this type of decay. This is log H versus the total strain introduced into the system when stretching a fiber. And he found that with an invariant with an alpha value, I forgot what alpha he used. It's in Wagner's paper in 1978, which you have in your references. It's a small value of alpha, so he basically takes the first invariant, which he always used, and a little bit of the other invariants. With this data, with this strain function, he can model the extensional flow data very nicely. So he used a second experiment to determine the strain function. Since alpha was a new parameter, he could use one format to describe shear and extension now. Sosky tried to use the same format and extended it to model three things: shear, uniaxial extension, and equibiaxial extension, and found that it doesn't work. You really have to compromise if you want to do that. Larsen did something similar in a paper with Kahn, and you somehow have a hard time to formulate the strain function have a simple representation of the strain function, and still accommodate several flows. So somehow, if you stay within one class of flows, you're okay with that modeling. But if you, for instance, want to model fiber spinning, where you have extensional flow in the entrance to the die, we have shear flow in the die, and then you have extensional flow outside in the fiber. and different ratios of those, have some mixed flows, then you don't know what constitutive equation you have to use. So model rheometry experiments might be safe with that approach, but complex flows have to be studied further. As the codes, the numerical codes come along now, as we can model complicated flows much more easily, I think we will learn how to change constitutive equations in those complex flows. So I think all of this is coming together. So if we wait long enough, or if we solve problems ourselves, that's an interesting area to work on. So far we had flows where the strain always increased in time, and that gave rise to a very simple formalism. We could say that H is simply the survival probability for a network junction between T and T prime in a deforming medium. You know, those junctions are falling apart because of Brownian motion. So with the time constants, if we wait long enough, they're falling apart. But a large strain is also causing a breaking of those junctions if we use that type of wording. And that's described in this type of function here. It gives rise to shear thinning or strain thinning in extension of flow. If the flow is with a monotonously increasing strain, like I plotted here, you can take 2 times, say, time t, where you want to have the stress, and a previous time t prime, and the maximum strain which occurred to this material is just given by the strain between t prime and t. That's the maximum strain you're getting in that system. However, if you have a flow where you go forward and then backward a little bit and then forward again, you have an increasing strain for a while and then going back, and then you're increasing the strain again. And the total strain, or the maximum strain, which has been supplied, which has been applied onto the network, is given not by the strain between T prime and T, but it's given by the strain at some intermediate time. Now, if the strain gives rise to a breaking of the network, a large strain at some intermediate time will destroy the network. So the characteristic strain for breaking the network will be this type of strain from here to here, and not the strain from T prime to T. We have to take that's the irreversibility assumption of Wagner. For describing the survival property between T prime and T, we have to take the maximum strain which occurred somewhere in this interval, and this might be at some other time, not just T prime and T, if you have some reversal in this deformation. Wagner formulated that by saying that H should be the minimum which we calculate by putting any strain in there between T prime and T. And any intermediate time would be determined with as a double T double prime in here. So that's important for calculating the stress in some complicated reversing flow mechanism. Such a reversal would occur at the exit of a die. You're extruding a strand from a die, and then the strand is shrinking, it's shortening in flow direction. So in the die, material elements have been sheared out, had been stretched, and then when they leave the die, they come back. So there's in all those recovery experiments, you have to accommodate that. There was a data set on such a recovery experiment. A strain has been imposed on a little piece of rod. Here, this from here to here. It had been strained, so this little fiber had been extended, and the flow had been stopped at that time. And from here on over here, the stress has been taken off, and the fiber has been allowed to shrink, has been allowed to recover. The total strain which occurs is given by the imposed flow here, and then as the stress is put equal to 0, by some recovery. It will not be total recovery, but some partial recovery. And that's the reversal of a strain history which we would like to model with the irreversibility assumption of Wagner and Stevenson. The data of Laun and Münstedt have been modeled this way. The recoverable strain is plotted over the total strain. So this type of strain, if this is equal, if this is equal to the imposed strain, then you have total recovery like in a rubber band. So the recoverable strain will never be equal. Will fall below this line here, and you see the data modeled very nicely with the strain function of Wagner, where the irreversibility has been introduced. So that's a very valuable concept. It is necessary. You have to imply that when modeling recovery or dice well experiments, for instance. The constitutive equation is fairly simple, so there's hope that it can be used to model polymer processing flows. I'm outlining one application which is quite interesting. Very symbolically, flow through a die is being considered where an extrudate comes out of this hole. In upstream here is an extruder which supplies fluid, and in this extruder you're imposing a wild strain history onto this material. You're producing all kinds of morphology, and it's questionable whether your material, which was exposed to all those strains, will give rise to a decent extrudate. Okay, so let's look at this problem. We would try to model the stress, which would be a measure of the flow-induced orientation in that system, and flow-induced molecular orientation would affect morphology. So we're looking at the stress here. And this stress is given as an integral from -infinity to the current time t by integrating backward along the streamline. In the simple model here, we would just take memory function, strain function, and finger strain tensor. You could split it up into two contributions if you would like to. We will decompose, again, this integral into an integral from -infinity to some time t0. Looking at this example, it's the contribution from the back here to t0. And a second contribution from t0 to t. That's the second integral. We will pick t0. We will pick this instant such that the contribution, so we have a first stress contribution and a second stress contribution. We will pick it such that this first contribution is much, much smaller than the second contribution, so that we can neglect this part of our strain history. We could say that the strain history from t0 on to t determines the instantaneous molecular orientation of a material element in the die or later on in the extrudate. But that the flow history upstream from here has no influence whatsoever on the stress, on the molecular orientation of the polymer. This fact by itself is the reason why we can produce nice polymeric parts in wild processing operations. If the material would memorize all the deformations, everything you do to this material during its processing, it probably would be very painful. You would get a horrible morphology. And there are some materials which have a very long memory. Polymer blends, liquid crystalline polymers, those materials are much, much harder to process. You have to be very careful with any processing history you put into this material. But if you process polyethylene or polystyrene, you have a very finite memory. And this is shown here in those constitutive equations. The memory is determined by the length of the relaxation time. You go along the streamline here, you go back as long as the memory lasts, and in a very slow flow, that will be, because the time will correspond to the longest relaxation time. However, in a flow of large strain, you only have to go back until the strain is large enough so that your H is going down, is decaying to 0, and then your memory has been eliminated by large strain in that experiment, and it's not eliminated by time. So strain thinning not only, that's very important, strain thinning not only reduces the stress levels in your machines, in processing machines, it makes processing possible because it wipes out any undesirable processing history which you introduce in a material in the extruder. Now you can invert that and can say the processing history in the final part, say in the extrusion die, is determining the molecular orientation, and you should design the extrusion die such that you get the desired morphology. That's where you really should invest into design, into details. That's the important part of the strain history. That's determining morphology. In calculations, you can take the whole integral. Here, you take the integral as it is, and you can integrate backwards further and further and further, and pretty soon you will find the position on the streamline beyond which the stress will not change anymore. You have a constant stress value, and you will see that beyond that the strain history is not important anymore. So you can determine the instant this T0 quantitatively if you have the rheological information. In summary, about those BKZ models, the strain energy function still has to be specified. We have to choose something specific to model polymeric fluids, and a proposal which was very successful is the factorized format, where we very easily can determine the time dependence from linear viscoelasticity. We determine the strain dependence fairly easily in a step strain experiments, or from viscosity from other large strain experiments we can determine the strain dependence. The calculations are fairly easy because you end up with exponential functions which you can integrate. It's somewhat messy occasionally, but it's still fairly easy to obtain solutions. The quantitative agreement with large ranges of experimental data are impressive. There are still deviations. It seems to be a big step in the right direction. And from that on, you can do some fine-tuning. You still can improve things further. H is somewhat flow-specific. You can determine this for shear flow or for extensional flow. And then you can model those flows very nicely. But we would like to have a general type of H which is independent of flow specifics. Indeed, for formulating a constitutive equation, you should have H somewhat independent. You shouldn't specify that. You cannot say I have a constitutive equation which only holds for shear, only holds for extension. It's limited in that sense. So we determine H experimentally in shear and extension, but we also limit our equation because of that fact. The irreversibility assumption has to be introduced into the BKZ model. This has not been realized by the original authors. It was a nice contribution of Wagner. And we also would like to know the contributions from the finger strain tensor and the Cauchy strain tensor. Probably do additional experiments, see how we would split this function into its two contributions, and then have more versatility in modeling the second normal stress difference, for instance, or the some extensional flow behavior which requires both of those functions. So in summary, this phenomenological approach has been very successful, has helped to make rheology quantitative. It is a heuristic approach. It's not a molecular approach. So I hope that in the next lecture we have some molecular aspects coming in when Mutu will talk about molecular dynamics of Rouse models and Edwards models. Thank you.